Hey, what's up, my chemistry people? Who is ready for a fantastic free response? I know I have been waiting all my life for this. I know I'm excited. A student compares some models of the atom. These models are listed in the table below in order of development from top to bottom. Boom. These models are listed in the table below in order of development from top to bottom. Boom. Part A. State the model that first included electrons as subatomic particles. Pretty straightforward, especially since you have all of this information provided to you in this data table. All we have to do is state the model, so my answer here for 1 point is the Thomson model. It was Thomson's model of the atom that he developed after working with cathode rays that we first discovered you could get smaller than the atom itself. Part B. State one conclusion about the internal structure of the atom that resulted from the gold foil experiment. Again, this isn't a trick. Use your data table, read, think. The one conclusion I'm going to come up with is an atom is mostly empty space. Again, the gold foil experiment completely revolutionized our understanding of the structure of the atom. Moving right along. Part C. Using the conclusion from the Rutherford model, identify the charged subatomic particle that is located in the nucleus. Again, don't overthink this. If you're simply asked to identify, just identify. The charged subatomic particle that's located in the nucleus is the proton. Boom. Move on. Part D. State one way in which the Bohr model agrees with the Thomson model. Again, a couple of different ways that you can take this. I think one of the most important ways that they agree with one another is that atoms have electrons. Boom. Man, we are flying. Okay. The student continued to investigate Dalton and his original postulates of atomic theory. One of the concepts that she explored was isotopes. Answer the questions related to isotopes and atomic theory that follow. Some isotopes of potassium are potassium 37, potassium 39, potassium 40, potassium 41, and potassium 42. The natural abundance and the atomic mass for the naturally occurring isotopes of potassium are shown in the table below. Take a moment, pause, look at that data table. Part E. List one of the postulates from Dalton's atomic theory that is no longer true due to the discovery of isotopes. Explain. One of the postulates from Dalton's atomic theory that is no longer true due to the discovery of isotopes is that all atoms of the same element are identical. That's no longer true. Now, let's explain. Although all atoms of the same element have the same number of protons, atoms of the same element can have different masses due to different numbers of neutrons. Boom. Part F. Show a numerical setup and calculate the atomic mass of potassium. All right, now let's keep in mind that weighted averages, or the formula for weighted average, is not on your formula chart. So it's an important one to remember for the exam. Not to mention, it's also important because weighted averages is how we figure out your grade in this class. All right, so it's going to be mass of the first isotope, 38.96, boom, times its percent abundance of 0.9326. Don't forget to move your decimal 2 places, plus the mass of your second isotope, 39.96, boom, times 0.0001. Again, don't forget to move your decimal 2 places, which means sometimes you have to include some zeros there as placeholders. Plus mass of the third isotope, 40.96 times 0.0673, close parentheses. Okay, now before I jump to my calculator here, again, keep in mind that as you solve these average atomic mass calculations, your weighted average is going to be closest to the mass of the isotope that's most abundant. In this case, potassium 39. So when I get my answer, I should expect an answer that's closest to 39. Let's jump to the calculator and see if that's true. Can't wait to find out. Parentheses, 38.96 times 0.9326, close parentheses, plus new parentheses, 39.96 times 0.0001, close parentheses, enter, plus 40.96 times 0.0673, close parentheses, enter. Our weighted average, 39.09 AMU. Exactly as we would expect, closest to our most abundant isotope. Boom! Takes us to part G. It says the radioactive isotope potassium-42 undergoes beta decay to form a more stable nuclide. Write the balanced equation for the nuclear decay of potassium-42. All right, I know the number on top. It gives it to me right here. The number on the bottom, remember, is my atomic number. Going to my periodic table, a trusty PT. Check it out, atomic number 19. Gonna put that at the bottom of my nuclide symbol. It's a decay equation, so there's nothing else. It's just this nuclide spontaneously breaking down. It's undergoing beta decay, which is essentially an electron with 0 mass and a -1 charge. As I think about what this turns into, the mass isn't going to change. Even though it's emitting a particle, the particle that's emitting is an electron, which is really small. Small. As I think about the atomic number of that substance, what number plus -1 equals 19? Answer, 20. Again, remember the sum of the numbers on the top on one side of the equation, so 0 plus 42, has to equal the sum of the numbers on the top on the other side of the equation. Same thing goes for the numbers at the bottom. Okay, before I finish, I need to know what is the symbol that's represented here. It's no longer potassium because atomic number is no longer 19. Trusty periodic table, bam, calcium. And you're looking at two beautiful points right there. All right, final part of this free response says list one of the postulates from Dalton's atomic theory that is no longer true due to the discovery of radioactive decay. Atoms of one element cannot be changed into atoms of another element. All right, that postulate is no longer true. Obviously, as we look at this decay equation. So this postulate is no longer true because radioactive isotopes undergo radioactive decay to become isotopes of more stable, different elements. And that's illustrated in the decay equation we've shown above. Free response is done.